In the name of Allah, the Compassionate and the Merciful. Hello guys. In this video, we're going to have an example about nonlinear dynamic analysis of structures with effects of uncertainty conditions as a material properties and section properties and element properties with Monte Carlo method. You see in here we have one element with 6 degrees of freedom. At the top we applied the seismic acceleration, and at the top we have a mass, and we have concrete confined properties and steel rebar properties as a stress and strain relations, and we use these three types of distribution functions for better estimating the real behavior of structures during the analysis and outputting the data to measuring the uncertainty conditions of this respected behavior. You see in here, so we have 6 degrees of freedom, one element at mass at the top, and we defined element properties and strain and stress properties and also mass properties as a distribution function with 1000 different numbers between, for example, this range to until this range for triangular distribution, and for example for these to these values as a 1000 random numbers, and at the end we calculate the maximum absolute value of displacement, velocity and acceleration of this degree of freedom number 4. So let's see the code, and for better explanation, so let's see the code in here. I use the random, uniform and normal and triangular functions in TCL language, you see, for better running in Opensees and finding the random numbers. So at the first, all data is going to be imported in here, and then 1000 increment as a random numbers is going to be calculated. You see in here, all data is going to be saved in a directory, and you see in here the length is used. I use the uniform probability distribution with this value as a minimum and maximum, and also the damper ratio. You see in here I use triangular distributions, and also for rebar size diameter, you see I use uniform, and also for mass I use triangular. So you can change it with your own. If you like, you can use just a constant number, okay? But in this example I use various use of these random numbers for probability distribution functions, and for better showing the result of these uncertainty conditions. So let's see the other input data which I used. For example, the cover of column, I used this value as a minimum and maximum with uniform distributions. So you see in here I use the compression strain with triangular distribution with these values, you see in here. And let's see the other values. For example, the confined to unconfined ratio, I use these values. So you can change with your own, for example, constant value, not random values. So let's see the other values you see in here. I use the steel rebar data and strain stress, and you see in here I defined the triangular distribution functions and so on. You see in here, let's see, yeah, in here we record all data, displacement, velocity, and acceleration of each process of in our increments with the random numbers. And you see in here we use this analysis for better converging the data, and we use Northridge acceleration record in our model. You see, let's see other values. Yeah, that's all. And for better converge, I use this method for controlling the analysis, and at the end it shows that the analysis is going to be steps with how many times. So let's see if I run this batch file at the end of 1000 increment, and all data is going to be collected in one directory as a data file. You see in here. So all steps, acceleration, velocity, and displacement is shown in here also. So if we use the Python code for better collecting and finding the absolute maximum values of this acceleration, velocity, and displacement, I use this Python code you see in here. And also at the end we have 1000 data of acceleration, velocity, and displacement. So what is the exact result? You see here we use various kind of probability distributions functions with different various numbers from minimum to maximum because we have uncertainty conditions of displacement and geometers and also the material properties. So we have 1000 different numbers, and so how can we manage it? I use the this method. For example, I use the histogram or even box plot for better finding the best displacement and best velocity and best acceleration of to finding our analysis. So I use the median of data. So if you want to find the better fit, in my opinion, we must use the median. So you can change and find other solutions. So if we run this code and see the result, you see in here in peak ground displacement we have different type of max in our analysis, and the data it's not normal. Okay, we have one peak in here, one peak in here, and one peak in here for peak ground displacement, and also for velocity you see the different peaks, and the distribution is not normal. Okay, so but you see that if we change our increments at 10,000 or more, we can fit it much better. Okay guys, and in my opinion I use, for example, this median data for peak ground velocity of our analyzing result of our analyzing of this structure, and also the peak ground acceleration. You see different peaks, one peak in here and so on. So you see in here that the peak ground the acceleration is not normal also. So you see in this analysis I showed you that if we use the uncertainty conditions for materials, elements, and so on, the result is not normal. Okay, it depends on your nonlinearity behavior of structures. So the result is going to be very complex, and you can get the exact behavior as a normal distribution function. You see here we have different peaks of this data, and for example, if I choose the best peak ground acceleration of this concrete element with the Northridge acceleration, I use, for example, this data as a peak. So one of yours can use this, for example. So it is various of data, and you can change it with your own, with different probability distributions, and that's all. Thanks, guys. I'd be glad to know about my modeling. Bye.